Okay, so hi everyone, and thanks for joining our weekly seminar. So today is really a huge pleasure to welcome Dr. Nanda Rea. So Nanda is coming to us from the Institute of Space Sciences in Barcelona. So a few things about herself. I will try to keep it short, even though it's really hard. So Nanda studied physics in Rome at the University of Rome Tor Vergata. Then she did her PhD again in Rome at INAF, but then midway she moved to the Netherlands with a Marie Curie Fellowship at the Netherlands Institute for Space Research, where she then continued working there until 2006. Then she moved to the University of Amsterdam with a Veni Fellowship, where she stayed until 2009. Then she moved for the first time to Spain, again with a Ramon y Cajal Fellowship, and then again to the Netherlands between 2012 and 2016 at the University of Amsterdam, where she had a very prestigious video work. And then since 2016, she's a staff scientist at the CSIC-IEEC in Barcelona, where she currently holds near C consolidator grants. So today she's going to talk to us about very, very exciting stuff. So Nanda, thanks again for accepting our invitation, and the stage is yours.
Thank you very much. Thanks a lot. It's a pleasure to meet you all. I'm sorry I don't see the chat nor all the participants because I have it the full screen, but I hope we will talk about about all the things later in the questions. So thanks for the invitation. Unfortunately not in person, but I hope it will be in person soon. Okay, so I will present you some, let's say, all the new results on the highly magnetic neutron stars. And somehow one of the things that I would like to try to convince you about at the end of my talk is that those are not just a few stars, let's say 30 objects we know in our galaxy, but strong magnetic fields, it's actually something which is important for probably most neutron stars that we know of. And as a consequence of it, most neutron star formations, so progenitors, and also many of the extragalactic transients that we see, like GRBs or superluminous supernovae, that actually are connected with the formation of those strong magnetic fields. So they're important not only for the few magnetars we see that we observe, but on a somehow larger astrophysical scales. So what I would like to convince you at the end of this talk, that all neutron stars do not look like this, but if you go very close to the surface of them, they would look something of this kind, which is actually an image of the sun, but in a different scale might be somehow interpreted as how the completely chaotic and strong field lines of a neutron star close to the surface would look like. And what I will show is that we do observe those surfaces, we do observe those chaotic field lines in most of the neutron star classes that we know of. Just to start, especially for students that might be new to this field, neutron stars science, it's something that theoretically started in the 30s, where first with the discovery of neutrons, and then soon after with the somehow theoretical ideas that starts mainly made, not only, but mainly made by neutrons, and at the center, and as a result of a supernova explosion, can actually be something extremely dense with the density of the atomic density and with the dimension, which is more or less 10 kilometers and the mass of the sun. Since the 60s, 1967, the first pulsar has been observed in the radio band, actually looking for different objects. And since now you see all the pulsar that has been discovered in the different surveys, which is at the moment are more than 3,000 pulsars. Despite the fact that we know more of 3,000 objects in our galaxy, there are a lot of things that we still need to understand and know about them from many different points of view. Very quickly, how they look like close, extremely schematic. I will not enter into this because it's very complicated and would be several talks or even a conference by its own. But one thing that I would like somehow to convey is that there are many things that we miss about our understanding on how actually a neutron star inside it's made of, especially in the core, where we have very little clue of what is in there. But one of the things that we certainly know that we observe the crust of it. So the crust of the neutron star, which is the part, let's say, outside, which is very hot, mainly shining in the X-ray band, this is something that we do observe and we do look. And this makes such that we are learning how this crust is made of. We know that that's how more or less electrons and ions and neutrons are somehow, and the currents are going within the crust. We know more or less the basic physics of it. And one of the things that I will show you in the next slides are many observations of the neutron star crust and different neutron star classes that are actually giving hints on which is the nature of those sources, and especially of their magnetic fields. Very basic, how do we measure the magnetic field of those sources? Very badly and very roughly. We simply assume that they are dipoles, and we absolutely know they are not, at least not only dipoles. But let's say from a rotational point of view, the structure that it's mostly driving the rotation of the sources is the dipole because of its dimension, because it's so big that the rotational property of the source are mainly driven by the dipolar emission. So from this, we can imagine that you have like a rotating antenna, and you can imagine then very roughly, and in this way, you can modeling in this way the neutron star, we can derive an estimate of the dipolar magnetic field, which is directly related with the period and the slowdown and the period derivative of these objects. This means that measuring the period and the period derivative, we can have an idea on the dipolar field, which I will show you is not the whole story on the magnetic energy of the source, but it's something important for the rotation. How those fields are formed, this is again, might be a conference by its own. There are many advanced that has been reached in the past few years, many simulations that now are, this is just one example, that are now really able to somehow trying to model what happens to the magnetic field of a core of a star in the first seconds of the formation of a proto-neutron star. And one thing that is extremely clear now, that we don't know exactly how these big dipoles are formed. We don't know how this is ordered together and how pulsars, the magnetic field actually goes from the few second simulation to the pulsars that we see now. But one thing that we do see in simulations, it's that the magnetic field has very strong non-dipolar component close to the surface just by formation, because it comes from possibly dynamo instability due to convection. And in some cases, there are also some ideas that there might be some fossil fields related to the progenitor of the star, but this is, again, not completely clear. But one thing which is sure is that actually from simulation, it's easier to create a non-dipolar field close to the surface, because it just comes from the convection and the instability during the formation, rather than having a very perfect big dipole ordered with the one that we actually see in the observation. This is a Pipital diagram. It's something that for pulsar astronomers, it's our daily bread. It's very interesting because there are many things you can derive from it. What you will see is the spin period in the x-axis and the first derivative of it in the y-axis. And in color, you see mainly the dipolar magnetic field formula that I showed you just earlier. And what you see is that on top right, you see the most magnetic sources. The one that you see circled are all what we call magnetars that I introduce in a second. We have different classes, extreme X-ray dim isolated neutron star. Again, I will speak about in a second. But one thing which is clear is that the slowest sources that we know of are actually the magnetars, and are also, you will see in a second, also the brightest sources, and also very young objects, which seems a contradiction, but you will see that this is not. Now, let me start. I will go to the different classes, some of the different classes, because many of them are actually similar objects, like the rotator transient and rotational power pulsar are the same thing. Mainly, I'm dividing these classes by what we think it's powering their emission. There are different energy budgets that the neutron star can have. Gravitation, of course, but we will not speak about gravitational waves in this talk. There is magnetic energy and rotational energy. Now, this magnetic energy, there are several waves in which you can be emitted. It can go in flares or magnetic reconnection. It can go in hitting the star itself. And depending on the kind of source that we're observing, we can check which is the physics of the emission we are seeing. So let me now concentrate in a second on the magnetars, which are the source, which are on top right of the Pipital diagram. 20 years ago, those sources were actually used to calibrate our X-ray instruments, because people observed these very bright X-ray objects with spin periods of a few seconds, very quiet, nothing really, really flaring or strange, apart from the fact that they have an X-ray, they were recognized to have X-ray luminosity, which were exceeding their rotational power, which is something that do not happen for normal pulsars. So this means that it was clear that those sources couldn't be only rotational power emitters, but there should be another energy involved in their strong X-ray emission, which was recognized to be the magnetic energy, because doing this PP dot game, magnetic fields around 10 to the 13, higher than 10 to the 13 were derived. Now, our idea of those sources changed drastically. So we know many of them. We know that they can be radio emitters, some of them, especially the very young and high dot ones. They have outbursts, so they are not steady sources, so they cannot definitely be used as calibrators for instrument. They show also hard X-ray spectra, so they are not just soft thermal sources, but they have very strong non-thermal contribution in their emission coming in the hard X-ray band, and they're extremely variable. And even more interesting, some of them actually do show very low magnetic fields. And I will show you this in a second, what exactly this means. So what do we think it's their emission coming from? So those are very bright X-ray emitters. We know that they have very strong magnetic fields. So mainly the emission that we see in the X-ray band, which is where most of their luminosity is emitted, it's due to the very hot crust that they have. They have this very hot crust because they have a very strong magnetic field in the crust, which is decaying actually and is releasing energy and heating up the crust itself. Now, those thermal photons, before reaching us, will pass through their magnetosphere. A magnetosphere of a source which has had such a big tangled and twisted magnetosphere, of course, it's more keen to have higher particle densities with respect to a normal pulsar. And this makes such that there are a lot of scattering that you can have from the thermal photons in the magnetosphere, that it's what is causing actually the non-thermal emission of those kind of sources. The other peculiarity of them that they show flares, big flares of similar of those that I'm showing you here. So below on the left are what we called the different flares, short bursts, which are on top in the left side. Then we have what we call intermediate flares or giant flares. Those are flares which are thought to be mostly non-thermal emission coming from magnetospheric reconnection or untwisting of the magnetosphere. On the right, you see some examples of outbursts of those sources, which means that often connected to those flaring activity, the source crust get heated up. That can get heated up very fastly in less than a day, and its X-ray luminosity increase by can be 2 or 3 orders of magnitude. So it shows what we call the long-term outburst, and then cools down in months or sometimes even years. All these effects are actually all related with the very unstable magnetic field that those sources do have. So you have this magnetic field which are tangled within the crust. So those magnetic fields can move because they are not in equilibrium, so they move elastically, and this can impart energy in the crust, and this means that you heat up the crust, but on the other side can also cause reconnection effects in the magnetosphere. So everything is somehow related to this very flaring and not stable activity that only those kind of pulsars do have, are related to their magnetic configuration and strengths. One example, just a few examples, just to show you some of the interesting things. Infinity object, this is one very interesting one, which is in the galactic center. It's actually less than a fraction of a parsec from the supermassive black hole. This is very interesting because it showed a very big and long-term outburst that here on the top panels, you see the models. Those are black bodies that we see a perfect cooling black body from the beginning of the outburst in 2013 till actually almost now. It's also very interesting for its radio emission, but I don't have the time now to review the radio emission of the source, which can be a talk by its own again. But one of the nice things is that we are really having a perfect black body just cooling down in time. And when you have a thermal emitters cooling down, like in general, even in whatever physical scenario, you can derive many things about the property of the material, which is actually undergoing this cooling. And this can be done by trying to model this cooling black body of those kind of outbursts of these sources. Those are some examples and some modeling. There are several done. And one of the things that doing these modelings of this outburst, as people realize, we realize, and other groups do realize, that there is somehow a limiting luminosity that they can reach. They are somehow standard candles. And the reason for this is that at certain point, you can dump a lot of energy in the crust, but when you go deep enough, when you pass what we call the neutron drip point, but anyway, when you go very, very deep, then whatever is the reaction of the crust, it will go in neutrinos, because this part is so hot that the neutrino emissivity is actually what is dominating the emission very close to the inner crust. This means that this magnetic reconnection, so this magnetic instability in the crust can dump energies of 10 to the 41, 10, 42, 43, 44, 45, 46. But at certain point, what we will see from the source is going to be dominated by the neutrino emissivity. So the photons amount will not reach higher than a few 10 to the 35 ergs per second. And this is something interesting because it makes them somehow standard candles, and this can be used to also to tweak the distance of those sources in the galaxy. It's also very interesting the relation of those outbursts and flares and fast radio bursts. Now, a direct relation, it's probably fast radio bursts are those very short, mainly extragalactic radio flares that are observed since 10 years, more or less, or almost 20 probably. And now it's clear that most of them are actually extragalactic. They are extremely bright, but it's also getting clear that we are seeing the tip of the iceberg of those emissions. So there are plenty of fainter fast radio bursts, either because fainter in nature or because fainter and closer, that we can actually detect with bigger telescope and can actually tell us a lot about the nature of those flares. One thing that was clear a couple of years ago with the discovery of a similar burst in connection with one of the flares of a very known galactic magnetars is that there is a strong connection between this fast radio burst and very young magnetars, probably in other galaxies. Probably not all fast radio bursts are going to be due to young magnetar flares in other galaxies, but many of them might indeed. And we have one example in our own galaxy. So this is also an interesting connection between those sources, because it's already telling you that there are many of them. There are many young magnetars in other galaxies, which we already know, because we know more or less the rate of the kind of a supernova explosion in those galaxies. But this is something that it would be very interesting to see a very, very young one just in our galaxy showing a very bright fast radio burst, as bright as the one that we see in others. And this will close many questions on those, but somehow these results are a first step of connecting those emissions that were thought to be different, which are magnetar flares and fast radio bursts, and actually they're not that different. Just to mention how very young magnetars in our galaxy look like, many of them are indeed radio emitters. Their radio emission are not exactly the same as typical radio pulsars. They have, in general, very variable spectra, mainly flat, but not all of them. They have very variable pulse profile, very variable luminosity. Their radio emission are connected with the outburst that we do see, so they are slightly different. It might be just because of a very different magnetosphere where this radio emission is actually formed. But one interesting thing is that many of the young magnetars in our galaxy are actually what we call radio magnetars. And one example, it's these new sources that were discovered a couple of years ago. It has, again, a huge amount of data in the radio. It's very interesting in the radio band, but I will not enter in this in detail. The only thing I want to point out that is very interesting, that actually is one of the youngest sources in our galaxy and is indeed a magnetar. How old magnetars in our galaxy look like. And this is one of the important points, that some of the old magnetars in our galaxy do have magnetic fields that are now of the order of 10 to the 12 Gauss. This means that they are not, this means several things. First, that many hidden magnetars in the pulsar population can be there, for which we measure a 10 to the 12 Gauss magnetic field, and we think their normal rotation powered pulsar might at certain point turn out to be a magnetar showing an outburst and flares. And this is something that happens to many neutron star classes that I will list just in a second. An interesting point of those low field magnetars is that the fact of having a very low dipole field, because it just decayed and it's an old source, makes such that we can somehow observe better the crustal component. So the spectrum of the source is almost perfect black body at 0.9 keV that was cooling down during the outburst. But during the highest phases of the outburst, a very nice structure, which is the spectral line that you see in the plot on the right, was observed, that can be easily interpreted with a magnetic loop and the crossing of our line of sight, which is what's given this shape of the line, that it's showing that this source, it's true that it has a dipolar field of 10 to the 12 Gauss, but it has magnetic loops that might reach even 10 to the 14, which is what is causing the outburst and magnetar-like activity of this object. It's not the dipole, but it's this loop close to the crust. Let me pass to another class of pulsars, which are slightly less magnetic. They have magnetic field around of 10 to the 13, not more than this. They are very close and almost perfectly thermally emitting neutron stars. They are called X-TINs. Also, they were used to calibrate many X-ray instruments. And one of the things that I would like to point out is that very recently, similar structures of spectral lines has been observed for these sources too, very similar of those observed in the low field magnetars, which is those are the phased versus energy and flux plots, very similar to the other one, where you see that there is a spectral line very phase dependent, which is somehow telling that it's due to a structure which is very localized on the surface of the neutron star. And again, if we do the same trick, if we interpret those lines as somehow cyclotron scattering in a loop plus rotation line of sight, we can measure the magnetic field of this loop, which is probably of the order of 10 to the 14 Gauss, while the dipole of this source is 10 to the 13. This is, again, another class of sources that do show some structures of magnetic field close to the crust. There are another class, which are called the CCOs. I see Danai raise hands. Go ahead.
Very fast question. How many X-DINs do we know now?
How many?
X-DINs do we know now?
7, confirmed 7.
Always the magnificent,
Always.
nothing more.
Yes.
Okay, thank you.
Probably E Rosita are gonna bring many more, hopefully. But for the moment, 7 confirmed. Yeah.
Thanks.
So another class are what are called neutron compact objects, which are very interesting sources because they are not radio pulsars. They are very bright and in the center of supernova remnant. One example is Casei, for example, which is a very well-known neutron star. And so they are very young because we see they are very bright remnants. They are a few kiloyears at most, more or less, but they are thermal emitting and not radio pulsars. And the interesting thing is that lately for 3 of them, a Pipital has been measured, finding sources which are here, as you see on the bottom left. Those are the one with the triangles are the CCOs. So they are very young, but their magnetic dipolar field, if you measure it with the Pipital, is only around 10 to 11 Gauss. This, of course, started a huge amount of questions about can we form neutron star at birth with low magnetic field, rather than being all of them at 10 to the 13, more or less, and then decaying to the different classes that we know, because those sources have a few kiloliter and they are already at 10 to the 11, which is, it would be too fast to decay from a 10 to the 13. But they're very hot. So this means that they should have a very strong field, something that make them that hot on the surface. And at 10 to the 11 Gauss magnetic field wouldn't be enough to give you temperature, which are of the order of a few percent, 0.2 or 0.3 keV on the surface. And one thing that has been pointed out is that one possibility is that they were actually born as magnetars, so with the 10 to the 14 Gauss, and had so much fallback accretion at the beginning that this material from the supernova has taken this magnetic field, being a supereditor accretion for a huge amount of time at the beginning, and just buried the field inside the crust. And then the field is now, when the accretion stopped, the field is now somehow trying to reemerge. So they're very young, they are very hot, they have a strong magnetic field within the crust, but the dipolar field that we measure is just 10 to the 11. So this was an idea that actually very recently, one of those sources, you see on the left, that those are 2 images by Swift in the X-rays of the big remnant of one of those, which is a very famous remnant, which is called RCW103. And at the center, you clearly see that the source underwent a very large outburst. These very large outbursts are actually what the only things that can cause them are a very strong magnetic field. Those are typical outbursts that you see that I showed you from Magnetars. Now, and even a more interesting thing of this source that it has a spin period. It has 2 kiloyears because the remnant has 2 kiloyears, and it has a spin period of 6 hours. Now, 6 hours in 2 kiloyears, it's an enormously slow spin period. To give you an idea, most of the isolated pulsars that we know now, that we know so far, has spin periods lower than 12 seconds. And this is 6 hours. So the only way actually to explain these 6 hours is that indeed, this source, it's still in what we call the propeller regime, because it had a lot of fallback accretion that buried the field, has the CCO were expected to. So, but the field in the crust, it's 10 to the 14 or 10 to the 15, which is what at certain point moving a bit because it's not stable can cause this outburst. And this source, it's still somehow in a regime which is experiencing some accretion, not directly on the crust, but on the magnetosphere. So it's in propeller. And this makes such that the spin period gets slowed down way faster than if it was in a normal dipolar emission. Rotational power pulsar, those are somehow better known. We know thousands of them. Some of them are also X-ray emitters, some of them are radio emitters, some of them are both, some of them are gamma ray emitters. So there are a large variety. A couple of them emits even in the TeV pulsed emission. Now, even in this case, in 2 cases in the past few years, we observed magnetar outbursts. And those are the 2 sources which are very well known to pulsar astrophysicists in general. In one case, this is also a radio emitter and a gamma ray emitter, which is the PSR 1119, that at certain point, it decided a few years ago to show an X-ray outburst. On top, you see 2 Chandra images of the pulsar wind nebula of one of those of the 1846 source, where you see how the central source got in X-ray in outburst a very strong luminosity. And those are, again, sources which are mainly rotational powered because they have rotational power of 10 to the 36 or more Hertz per second. But at certain point, their magnetic energy makes such that it does a big outburst. So somehow what I wanted to show you with all this is that all the classes of isolated pulsar that we know of had somehow showed strong magnetic fields close to the crust, either by directly undergoing an outburst, so an increase in luminosity and then a cooling decay, or by showing, like in the case of the X-teens, this small structure via spectral lines, very phase resolved. Now, why this is important? This is important because magnetars are related with the most energetic transients that we know in the universe. So this is somehow a recollection, a very schematic recollection on how transient timescales versus average luminosity goes. And you see that many of them, apart from the magnetar flares themselves, which are already very bright, many low luminosity GRBs or some long GRBs or low luminosity supernovae can actually be strongly related with the formation of newly discovered magnetars. So we want to know how many magnetars can we have in our galaxy. So in how many pulsars the supernova and the progenitor are actually should form a strong magnetic field to start with, especially close to the crust. Then the dipole, we don't care because you can have accretion, you can have many things that can somehow change your dipolar configuration. But how many progenitors, how many explosions of supernova should be able to form a 10 to the 14, 15 core? And this is something somehow related on how many magnetars and how many magnetar flares we expect and have in our galaxy. This is just to show you, this is the neutron star population that we know now, so that we observe. Those are more or less 3,000 sources. You can clearly see the 2 Magellanic clouds in here. But if you do some simulations with population synthesis, it's very clear that this is what we expect. So we should have in our galaxy between probably around 10 to the 7, 10 to the 8 pulsars, of which we are really seeing the very, very high tip of the iceberg. So there are plenty of information on this population that we should try to derive, especially then for planning future surveys with instruments which are even bigger. One of the problems, for example, of that soon people realize of having all these different classes of the X-teens, of radio pulsars, of magnetars in a different and not evolutionary scenario, is that we would definitely run out of supernova explosion of core collapse to form them. So if we consider all of these different neutron star classes as separate, so not evolving one to each other, we would need almost one order of magnitude more core collapse supernovae in our galaxy than what we do expect and what we do observe in other galaxies, which is more or less a couple per century. Now, another things that we have learned in the past years that I showed you now is that somehow non-dipolar component and strong magnetic field are somehow ubiquitous in the neutron star that we have in our galaxy. Now, how do we solve in this way this supernova rate problem? Why this is somehow solving something in this scenario? Because if we consider neutron star evolution, which means doing models on how the magnetic field and the thermal crustal properties evolves from birth till several mega years, till let's say 10 mega years, which is more or less the age of the pulsar population we see, we soon realized that actually all those different classes of pulsars are not independent. So depending on how you form them, they can pass to different stages of their life where you either are rotational power dominated, or like the PSR 1119. So you see a very strong radio pulsar that at certain points, the magnetic field decays, rotational powers are emitted and decays, and it might turn out to be an old magnetars because the crust of the surface just keeps being thermal. So you can transform somehow one class to another. And this means that their evolutionary scenario, you do not need to have so many core collapse supernovae to form them all, because they will go evolutionary from one kind to another. Some example, those are some of those simulations that are done from, there are many groups that are doing similar simulations. This is, I'm just showing the one that we are doing. Here, what on the left, this somehow both are a slice of the neutron star where we inflated the crust. You see in white the dipolar component of the crust, and in violet and yellow the toroidal, let's say the toroidal field, the non-dipolar component of it. And what it's clear, and then on the right some panels on how this source would evolve in time. Time is running, how this source would evolve in time in the Pipital diagram and in luminosity. So this somehow shows that depending on which is the configuration you start with, you can end up with an X-dins, you can end up with a magnetar. A magnetar can end up an X-dins, just going, being old and getting old and releasing most of its energy. So they will get fainter, but still somehow hot to be observed. And this solves the rate problem and also solves the understanding on the connection of the supernova classes in our galaxy. Just showing you some of the plots, just very quickly. Those are again, for example, the PP dot with some of the curves that you would expect for different magnetic fields. So in red, you see cooling curves for strong magnetic field, and then for lower. And on the other side, you see how in the age and luminosity you would expect this source. And many of these sources, actually, we do see them where we expect them to be, and being simply related evolutionarily to different classes. Now, to finish, I would like to mention, because in all this scenario, in the past couple of years, I would say, some interesting sources has been discovered. So which are in particular 3 objects, which you see. The first one to be discovered are this PSR J0250, if I recall correctly, by Lofer. And then other 2 sources has been recently discovered to be neutron stars, actually magnetars, so with strong magnetic field, but with spin period which are extremely long, very long, as you see, compared to the whole population of other pulsars that we know in our galaxy. Now, what make those sources being somehow radio pulsars with high magnetic field and so with periods which are so long? The only way somehow to explain them, which is not even that complicated and then strange, it's to being passed, as in the case of the CCOS, a fallback accretion during its supernova, during its formation. So this is another ingredient. So the pulsars in our galaxy and the neutron star in our galaxy, their emission is not only driven by only magnetic field configuration at birth and age, but also there is some of them which could have a strong fallback at the beginning that depends on the progenitor star that we can observe actually going somehow in a different direction compared to the class, but there's nothing really different in there, just only that the parameters of the accretion rate and the magnetic field with which they start with were such that they could have a history of accretion at the beginning. Now, we recently did some simulations of this just to show, this plot was not supposed to be here, sorry, let me take it out. This is the good thing of being online. So this is some easy simulations that we did recently to explain those two very slow pulsars, one with 75 seconds and the other one with almost 1,000 seconds, that on the left side, you see the spin evolution of 4 different accretion rates that you see in color with fallback accretion rates with magnetic fields at birth, which are in 4 different ranges. It is already clear from here that if you want to reach something which has 1,000 seconds, then you need a strong magnetic field. Otherwise, there is no way, even with the accretion, to explain such slow pulsar. You need a strong magnetic field and an accretion at the beginning. The accretion at the beginning, what it does, that you see in the plot low right, it's to slow down, make your source enter in propeller, which is the solid line that you see. And when the source enters in propeller, that means somehow that you are accreting on the magnetosphere of the source. This will give a torque to the spin period, which is so big that might slow down very easily in 10 to the 4 years, so something young, to 1,000 second pulsar. And this is probably what is happening to this very slow pulsar that has been discovered lately, and probably many of them will be discovered with future, in future surveys. This doesn't mean that all pulsars should undergo this kind of slowdown. Actually, they do not. This just depends on a certain range of parameters of m dot and magnetic field at birth that might or not make your source enter in the propeller phase and then slow it down in this way. So this is somehow an additional scenario that it's important to consider when one looks at, in general, at the neutron star population in our galaxy. Okay, to conclude, I tried to show you how somehow some observational results that shows that magnetar-like activity, it's very common in the neutron star population in our galaxy. Is not just what earlier were thought to be somehow these 10 weird bright X-ray sources that they were calling magnetar, but magnetar-like emissions of bursts and flares are observed even for rotational powered pulsars. And it's also important somehow to connect all these different classes, because we want to know how often a strong magnetic field is formed in neutron star in a galaxy. Also because this is connected with transient rate in other galaxies that we want to study. So it's important to know which fraction of magnetars we have, let's say, which fraction of sources that might show magnetar emission we have in our galaxy. And the only way to study this is to do evolution simulation of field evolution in the end population synthesis work. And this is something that it's on its way, and there are several groups that are doing it right now. And so I hope I convinced you that this is an interesting field to work on in general, because every day there is something new, there are new discoveries, and more will come very soon with a new instrument like CSIC-IEEC or well, Athena in 10 years. Okay, thank you very much.
Many thanks, Nanda, for this very clear and interesting talk. I see a few people are clapping, so I'm gonna clap as well. So Any questions for Nanda? Please raise your hands or speak up. I see a couple of hands raised already. So Costa, please go ahead.
Hello, thank you very much for this talk.
Hello.
I'm Konstantinos Kovlakas. I wanted to ask you about this fallback scenario for the long period pulsars. It's something that we don't usually consider when we're doing population synthesis studies. I'm wondering if there is an observational proof or, let's say, evidence for that, because I would suspect that this fallback mass would also increase the mass of the neutron stars, so they would have systematically higher masses. Is my understanding correct?
So in general, so there are plenty of studies that has been done by several groups just studying how, from a supernova point of view, how much material you expect to have in a fallback. Now, the amount of material that you expect to fall back, it's maximum something like 0.1 solar masses. So this is 0.1, 0.2 really at the maximum. So this is somehow, this is not a problem in the sense for, it will not go and accrete and have a supermassive neutron star because it's just not enough in general. It's also true that how many pulsars are expected. So what we know for sure is that fallback exists. We see fallback in supernova remnants, traces of it. Every supernova simulation shows that there is a material that falls back. So this is something that do exist and we have to cope with it. Now, the amount of material you fall back and the magnetic field of the pulsar you form can make such that you then at the end, if you look at the pulsar evolving, you don't even realize that it had some fallback. For example, if you have a very small m dot to start with in the fallback, because this progenitor does not have, that depends a lot on the geometry of the explosion on many parameters. So it will depend from pulsar to pulsar. So in some cases, the m dot, it's low, your magnetic field is low, and your pulsar will be has a rotational power than in ejection somehow the whole its life. So you have your normal pulsar population. In some cases, especially if you have a high m dot and a strong magnetic field, you might be in a regime where you can experience, and your evolution of this pulsar do have to take care about this, because you slow down the pulsar more than what would be just by the dipolar losses alone. Now, how many of the pulsar population do have, for how many this occurs, I have no clue, I don't know. It's very difficult to constrain this at the moment with the observation, because the observational bias that we know we have in detecting slow pulsars makes such that the population of very slow pulsars that we have, we don't know how much. We cannot say, okay, we see 2 slow pulsars, we see 3,000 normal ones, then this is the ratio. No, because there are so many observational bias to detect those low pulsars, which can be high band pass filters in radio observation, can be that our surveys, most of them just last for very short time in a certain part of the sky, and you don't detect the slow ones. So it's very difficult to model those. So at the moment, it's not clear how many, which is the percentage of sources that would show this fallback with respect to the one for which they will have some fallback, but it's just not affecting their period evolution.
Thank you very much. So yeah. Thank you very much. So I suppose it's a lower limit, and possibly it needs detailed modeling of the pre-supernova stellar structures, theoretical studies.
Well, I see the point is that I don't see this coming from a supernova modeling point of view anytime soon, in the sense that in order to know this, those fallback accretion will need to be modeled properly for years after formation. And this is something that at the moment, proper simulation are not really able to do so. But so we are stuck with the analytical estimation for the moment, I would say.
Thank you very much.
Thank you, Costa. So Nick Kilafis, please go ahead.
Nanda, thank you very much. Very nice review. I learned a lot today, and I must admit that in the last 5 or 6 years, I stopped working on magnetars and stopped reading papers too. So I see that I have lost a lot. Yeah, nice work. And I may come back to it.
Thanks.
Yes, really, thank you. Now, let me ask you a clarifying question first. Any of these classes that we discussed, is any of them in binaries, or they are all isolated neutron stars? Isolated.
They're all isolated, all of them.
So one thing that I lost over the last 5 years is that back up to 2015, fallback disk was a bad word for the magnetar community. It was a forbidden word. Now you see that the community is using fallback disks left and right to explain things. So that's an interesting development, very interesting indeed. And that leads to my question. As you know, my work on magnetars had the opposite view, had the accretion from a fallback disk. And the models were dismissed by the community, so much so that we had difficulty publishing our papers and so on and so forth. So I'm asking now you, who seems to have an open mind about these things, why is the fallback disk model dead for magnetars? In other words, what if you want to throw 0.1 solar masses onto a neutron star to increase its period, what's so difficult to dump an Earth's mass? Orders of magnitude smaller, 1,000,000 times smaller, or 100,000 times smaller, to produce the observed X-rays. So yes.
Okay. I think that the one of the big killers of the fallback disk, in the sense, not the fallback disk that you have slowing down in propeller, this is not the luminosity, this is the spin down, it's something different. Yes. So in those cases that I was mentioning for the slow pulsar, the fallback disk, it's not responsible for the emission of the source. It's responsible for being the material around and slowing down the pulsar. In the case for which the fallback disk were claimed has accreting on the source to explain a 10 to the 35 ergs per second emission. Now, I think that the main killer of it was the discovery of radiomagnetars. Now, radiomagnetars that now we know, I think more or less 7 of them, are sources for which you see a 10 to the 34, 35 ergs per second X-ray emission pulsed simultaneously with its radio emission. This is not something that you can have if you're accreting on the surface of the source.
No.
And you need to accrete on the surface to have the X-ray pulsations. Otherwise you couldn't.
It is written in the paper with first author Joachim Trumper back in 10, 11, 12, 13, something like that. I don't remember. That you can have the flux tube that takes matter from the fallback disks and puts it on the magnetic pole is quite narrow. So the footprint of accretion is an area of 50 to 100 meters, when the polar cap is 1 kilometer. So you can have radio emission. So of course, when you have accretion, you short circuit the radio emission. So you cannot have from the same region the two, but nearby regions one can have accretion and the other have radio emission. For example, it can rain in an area in a small area of town and have sunshine in another town, in another part of the town. But, so it is not a killer. It is possible.
But we know which is the region emitting the radio, because we can connect the profiles of the X-ray and radio, and they are all very well aligned in most of the sources. This means that somehow it's the same region emitting the two.
Yes.
And on the other side, then this should happen also for millisecond pulsar, and it does. It does it.
Is your accuracy smaller than 100 meters or a kilometer?
A kilometer might be 100 meters now. A kilometer might be.
Then you can have 100 meters accretion, 100 meters radio emission next to each other.
I don't know. I'm not saying this is something we don't see in accreting sources, because in principle, you might be able to see the same thing in recycled millisecond pulsar, and we don't.
Oh, in Hercules X1, the polar cap, the accreting, the footprint of the accretion is 1 square kilometer. So there is no region left to have radio emission. In normal accreting X-ray pulsars, the accreting area is huge, huge meaning 1 kilometer. So for nothing is left to emit radio. If radio is emitted, as we have seen in some X-ray pulsars, comes from the magnetosphere, comes from further out. Anyway, okay, I heard what you said. I will read some more and come back to it. But let me ask you, how secure do you feel about using the PP dot formula for the magnetic field, for the dipole magnetic field? You said that there are many multiples, and yes. So how secure do you feel using the PP dot formula?
Let's say I'm less secure about the opening angle, less secure about the orientation, less of B with respect to P, which it's something that in principle you should consider in this formula. So there are other things which are, I would say, less secure, but on a, let's say on a larger, let's put it this way, it's true that there are plenty of multiples, and there are surely plenty of multiples in all pulsars we know. And many of them, those multiples can be strong field, can be of the order of 13, 14 Gauss, yes, but they're gonna be very close to the crust. This means that whatever happened to the P and the P dot will not care much about the multiples, but will care about the dipole. So
I agree,
because it's
I agree, but so
this is why I'm less comfortable to say this is the exact formula, simply because of I don't know the orientation. I don't know how the angle between B and P evolves in time, because it does. So there are many things I don't know, but let's say it's a good estimate for the dipole, which doesn't mean it's a good estimate for the whole magnetic energy of the source. There's no.
I agree, but the PP dot formula assumes that the neutron star, the magnetic neutron star, is in vacuum. If it's
yes, vacuum, this is also another problem.
And there is a fallback disk, it does not hold.
Yeah, that's true. This is another problem.
Last quick question. You interpreted, not you, I forget his name now, 2013 Nature paper, the cyclotron line as proton.
Yes.
Right, Tiengo, yes. As proton cyclotron. Why? Yeah. If it is electron cyclotron, it is 3 orders of magnitude smaller magnetic field.
Yeah, this is, I mean, it might be. Let's say it might be, and
but this is the only.
It might be. The point is that you don't expect those kind of multiples. You somehow expect them to have a magnetic field either equal or stronger than your dipole. This is the only reason for which the proton was used, but we definitely don't know this for sure.
It is not. It just fits the picture, nothing else. In other words, if you use proton cyclotron, you get a strong magnetic field. If you use electron cyclotron, you use a weak magnetic field. That doesn't fit the picture. But
you need the strong magnetic field. You need the strong magnetic field because we have flares that reach 10 to the 41 Hertz per second with a time scale of half of a second.
I agree. I agree. The particular.
So we know there is a strong magnetic field somewhere in there.
Absolutely.
And this is the place where this might be.
We agree 100% on that. If it cannot be anything else than magnetic field to explain the burst. Absolutely nothing else. But my question is, that particular measurement, why is it a proton cyclotron and not an electron? That's all I'm asking.
It can be like, it's a proton cyclotron simply because we are looking for a strong magnetic field in this source, and this was a possible place, but it can be an electron. I agree.
It was an exciting talk. Thank you very much, Nanda. I have many more questions, but I will stop here. Next time I find you at a conference, we can have a long discussion. Thank you very much. Thank you.
Sorry, I was muted. So thanks, Nick. So I see Danai has her hand raised. So maybe the last question.
Okay, thanks. Hi, Nanda.
Hello.
Now, actually, I had one question, but now I have two. So I wanted to ask you something back to what Nick said.
Mm-hmm.
So for the ones that we see radio emission and X-rays, though, and they are aligned, the profiles, don't we see any correlations between them that could also show that it's not the case that you have like a hollow cone emitting radio, and in the middle you have this accretion column that emits the X-rays?
Sorry, say it again. Which kind of correlation you're?
Correlations like between the intensities and the shape of the profile and the variations that you see there.
That's very complicated in the sense that so in the X-ray band, in order to construct a profile, we actually need for the luminosity of those sources, we might need something like 10,000 seconds. In radio, in 10,000 seconds, the profile of the sources usually changes, because they are extremely variable. And
okay, so you wouldn't see anything on short time scales.
I mean, any profile variability on short time scales in the X-rays, we miss it actually. Yes. Yeah. It's also true that in general, the X-ray emission of those sources are pretty quiet in the sense that they come from a hot spot. So it's a black body. They are very broad in shape, or one black body, let's say a temperature map, which have a single hot part, and then it rotates. In radio, it's different because this comes from a magnetosphere. It's a bit higher up. It's lined, but it's higher up. And it's a complete mess in there. So this is why there are a lot of currents, and this is why the profile is changing that much. So I'm not even sure that we actually do expect a similar profile variability in X-rays, although we do not resolve it. We cannot observe a profile in such short time scale anyway. But it might be that it's just more stable because the emission part, it's more stable in X-ray in this sense.
So my actual question was, can you please go back? You had some preliminary results with the trajectories in the Pipital diagram. I think it's slide 34, maybe. No, much further, sorry.
Yep.
These ones, can you make it a bit bigger? So
yes.
I'm trying to see the axis and the scale that you have. So my impression is that this gives you, what would it be? What breaking indices should we expect from this? I'm trying to, I mean, is this plot, what will an n equals 2, will it be a horizontal line for the evolution?
No, and this n equals 3, it's the typical one. So in this case, the point is that the breaking index for will not be 3, and it will change because the field is decaying.
Yeah, I see that, but I'm trying to understand where would the n equals 3 be in this plot. So are they steeper? In general, they seem to be steeper.
So at high fields, they are steeper, yes.
They are steeper. So yes. It's, okay, so it's going to be smaller breaking indices that you predict here.
Yes, yes.
Okay, thanks.
Yes, but this doesn't mean necessarily that if you measure a small breaking index, this means that you have a strong magnetic field. This is not this way.
No. Whatever you measure with a breaking index, I wouldn't take it like as a, anything.
Yeah,
really
these sources have so much timing noise and so much variability in the amount of particles in and out outbursts in the magnetosphere that your long-term breaking index is going to be impossible to measure because your p dot dot, it's varying a lot. So there's none of these sources have a proper breaking index measured because it makes no sense. It's impossible.
Sure, yeah. Thanks.
Okay, thank you, Danai. So I think we ran out of time. So Nanda, thanks a lot for the talk and the interesting discussion. And let's try to repeat this in person next time.
Yes, please.
Okay, so I'm gonna stop the recording, and so thanks everyone for joining, and see you next week. Bye.
Thank you very much. Bye-bye.
Bye.